Hello everyone. In this video, we're just going to give a short introduction to some properties of relations. So in this video, every relation that we talk about is going to have the domain equal to the codomain, so A will equal B. And because of that, we can make our arrow diagrams look a bit different. So I'm going to start with an example and show two different ways to display its arrow diagram. And then the latter is kind of what we're going to use throughout because the domain is equal to the codomain. So in this case, let A be the set just 1, 2, and 3. And then we'll define the relation R on A. Again, because it's only the one set, we'll just say that R is defined on A, not like A cross B, by a pair is in the relation if X is less than or equal to Y. So the first way that we could do this is just as we have been doing, right? So we've got like 1, 2, 3, and in this case, it's the same set both ways, so gonna kind of mirror each other. And then, right, so 1 is less than or equal to everything else. So 1 is less than or equal to 1, 2, and 3. So there's an arrow to all of these. 2 is less than or equal to 2, and less than or equal to 3. And 3 is only less than or equal to 3. Okay, but we can make this actually a little less complicated looking because both sides are the same. So what we can do is just draw 3 nodes, 1 for each. And so 1 is less than or equal to 1. We just draw an arrow back to itself, right? An arrow to 2 and an arrow to 3, right? 2 also less than or equal to itself, so we can draw that arrow. And then to 3, and then 3 less than or equal to itself. So we just have these loops, and then here, because they're just the same elements, we don't need to have 2 different sides, but rather can just have 1 dot for each as opposed to 2. Okay, so we're going to be doing things like this for the rest of this short video. All right, so let's do one more example here, and I'm doing these 2 examples for a reason that we will see shortly. So here, A is just the set with the elements 1 and 2. And we're going to define a relation on the power set. So we're going to have 4 vertices here. I'm going to draw them this way for a reason. So we've got 1, 2, and then of course the whole set, 1 and 2. And we define the relation by there's an arrow from X to Y, or XY is in R, if X is a subset of Y. So the empty set is a subset of everything. So there's an arrow to itself. There's an arrow to all the other things. 1 is a subset of itself, of course, and belongs in 1, 2. 2, subset of itself, and belongs in 1, 2. And then finally, 1, 2 is just a subset of itself. So I want to have this, and I want to have the one we previously talked about here on the same page. So both of these are what we call order relations. And you can probably see some notion of order here, right? We have like a hierarchy, and hopefully like less than or equal to or subsets make you think of some sort of hierarchy, right? Like 1 is the smallest here, and you kind of go up in number here. And here we're kind of going up in cardinality, right? Like 0 elements, 1 element on this tier, and 2 elements on this tier. And then something that we'll explore a bit more in class is the difference between these 2 things, namely on this side, right, you can compare all 3 of these. 1 is less than or equal to 2, 2 is less than or equal to 3, 1 is less than or equal to 3. You can compare all of them. But notice here, this middle tier, you can't really compare the set 1 with the set 2 because neither is contained in the other. And so there's a little bit of a difference here, but both of these have what we call a partial order. And so that's the last thing that we're going to talk about here. So a partial order is a relation R on a set A satisfying 3 properties, and we're going to see how these previous examples fit it. So 1, it is what's called reflexive. This means that AA is in R for any A in A, aka there's always a loop from anything back to itself, okay? And of course, we saw that on the previous ones, right? That basically A is always less than or equal to A, or some A is a subset of A depending on the context. That's always true, and so we always saw loops at each point. Second is that it is anti-symmetric. So to think about the definition, I want you to think about how less than or equal to works. So if x is less than or equal to y, and it's not equal to y, then it's always going to be the case that y is not less than or equal to x, right? It doesn't go both ways, right? 2 is less than or equal to 3. It's not equal to 3. We wouldn't say then that 3 is also less than or equal to 2. And so this is basically the property that we want to be satisfied so that it makes sense with order. So this is if AB is in R and A is not equal to B, then BA is not in R. Basically, if there is an arrow from A to B, like we saw in ours, right? So there's like an arrow from 1 to 2. But there was no arrow back from 2 to 1 because 2 is not less than or equal to 1. So that's basically what goes on. If there's an arrow one direction, there is not an arrow back. And then the final thing is transitivity. And this should also make sense. Basically, right, if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C, right? And so that's the last property, and this is just written if AB is in R and BC is in R, then AC, is also in R. Basically, what we saw again with 1, 2, and 3, there's an arrow from 1 to 2, there's an arrow from 2 to 3, there was also then guaranteed to be an arrow from 1 to 3. Okay, so all three of these properties must be satisfied, and then we have what's called a partial order. By A. All right, so we're going to finish up with one last example here, and then an exercise. So we're going to define a relation R on the positive integers by saying that there's an arrow from A to B if B is divisible by A, right? So like, there would be an arrow from 2 to 4 because 4 is divisible by 2, for instance, okay? Okay, so we want to check, is this a partial order? So first, is it reflexive? Well, anything is divisible by itself, right? So like A is divisible by A, it's just A times 1. So that means that AA is in R, or there is always a loop at any point A. So next, is it anti-symmetric? So in this case, right, we suppose that there is an arrow from A to B. So suppose AB is in R and that it's not a loop. So basically that B is not equal to A. Then the question is, do we have an arrow back, right? Well, this means that B is equal to some AK because B is divisible by A. And since they're not equal and they're both positive numbers, K must be greater than 1. What does this mean? This is going to imply that B is greater than A, right? And so it's impossible for A to be divisible by B. Not possible for A to be divisible by B. Okay, and so that means that BA is not in R, and so yes, it's anti-symmetric, it is reflexive. And then the last one would be, is it transitive? So here we assume we have an arrow from A to B, we assume we have an arrow from B to C, so that means C is divisible by B, aka C is some BK, and B is divisible by A, and so B is some like AL. So then the question is C divisible by A? Well, yeah, we can just substitute in, right? So C is AL times K, or A times LK, so C is divisible by A. And therefore, we have an arrow from A to C. Okay, so this just says if AB is in R and BC is in R, then AC is in R. So it satisfies all three, and thus is a partial order. All right, and so for your exercise, I want you to determine if this relation here, defined by there's an arrow from A to B, if the absolute value of A is less than or equal to the absolute value of B. So in this case, this is different from the previous one in that like there would be an arrow from 1 to -2, because even though 1 is greater than or equal to -2, its absolute value is smaller. I want you to check if it satisfies these three properties or not. All right, thank you for watching.